We have a couple more cases. One involves something pretty crunchy, and that is finding antiderivatives of inverse trig functions. Right? We know how to find derivatives of inverse trig functions. We know how to find antiderivatives of expressions that lead to inverse trig functions, but we haven't talked about how to find the antiderivative of an inverse trig function itself. All right? So you go through your list of possible approaches, and one approach that may not seem obvious but is actually the correct approach would be integration by parts, because it's not a fraction, so partial fractions wouldn't make sense. All right, we're not dealing with any radicals with variable expressions, anything algebraic, so trig substitutions wouldn't work. We don't really have much in the way of useful identity replacements for arc secant. So our best bet is to go with something that we do know, and that would be integration by parts. So let's go down that road. All right. If you remember integration by parts, we want to select a u that is something that we can differentiate, and a dv which is something that we can anti-differentiate. Well, we're here because we don't know how to anti-differentiate the arc secant, so we better not make that the dv. All right, so that's got to be the u. Ideally, whatever you select to be u would become simpler when you differentiate it, and whatever you select to be dv would not make things anything more complicated when you anti-differentiate it. You can't always get what you want, but that's the goal. All right. So the only thing left over is a dx, so that's what dv has to be. So we would say v is equal to x. If I differentiate, I get du is equal to, oh, we could say du dx. We'll do that first. We're just going to move it over anyway, but this is going to be equal to, it ain't going to be pretty. So 1 over the absolute value of x times the square root of x squared minus 1. All right, and that goes back to this relationship here, except I'm saying that the u is really the x. All right, so the derivative of x would be 1. So x, and then there you have it. All right. So we got all that going on. So uv minus the integral of v du is going to be x arc secant of x minus the integral of v multiplied by du. Now, we've learned previously that the du we're going to get just by moving the dx over to the other side. Oh, you know what? I said I was going to write the intermediate step, so I'll stand by that. I'll throw this in a new step. All right. And so v du is going to be x over, well, really all this other stuff. So it's really just a question of, okay, well, where's this going to end up? We have to continue the process and evaluate this integral. We'll have to address this piece here, but we'll get to that in a minute. What I'm looking at first is this. That looks like something that can be evaluated using a trig substitution. All right, that's in the form of u squared minus a squared. All right, so u would be equal to x, a would be equal to 1, so I'll draw a triangle. All right, so hypotenuse, adjacent, and that would give me my missing side. Ooh, let's make that look halfway decent. Square root of x squared minus 1. All right, so when it's in the form of u squared minus a squared, we think secant. All right, so secant of theta, and that kind of makes sense. We're dealing with the arc secant derivative. So x over 1
So x is equal to secant of theta. Dx would be equal to secant theta tangent theta d theta.
All right. So then my secondary function is going to be the ratio of the radical to the constant.
So opposite side, adjacent side. So it's tangent. So the square root of x squared minus 1 over 1, which is the same as saying the square root of x squared minus 1 equals tangent theta. All right, so I can make that substitution. And I can swap out an x for a secant theta, each instance of x. And I can swap out the dx for that whole shibiggity bangity boom. This one over here. Alright. So we'd be looking at x arc secant of x minus, big old mess, secant theta over the absolute secant theta tangent theta, then secant theta tangent theta d theta. Alright, so off the bat I can cancel a tangent theta. It does beg the question of whether I can cancel a secant theta, so we'll get to that in a second. I'm just going to sketch out a quick look at the unit circle, but only really the top half, because that's the only part that's relevant, because the arc cosine and arc secant functions are restricted to the interval of 0 to pi. Alright, so if we look at the circle and just, kind of choose any sort of arbitrary value along there, or location along there. One of the things about the secant function is that we are calling the hypotenuse the unknown. Alright, so we're calling that x. And we're calling the adjacent side 1, so actually we're living beyond the circle. So the adjacent side is 1, and we're looking at something like this. Alright. If I can make that look halfway decent. And actually, let me put these off on the side where I had the 0 initially. Alright, so the hypotenuses are unknown now. And the missing side here would be the square root of x squared minus 1. Alright. Now, if I move this into the other relevant part of the restricted region, let's say somewhere over here, we could get a negative result for the arc secant. Right? The only issue is it's like what is going to be negative, So the hypotenuse is always going to remain positive. This vertical side here, just based on the geometry of it, is always going to remain positive because it's above the x-axis. All right. The only thing that would change in sign would be the adjacent side. So this would become a negative 1. All right. So if I apologize, the arc secant wouldn't necessarily become negative. It's the other ratios. All right. So I can pull a sine function out of this, or a cosine function, or a tangent function, and even the arc secant, but I didn't want to limit it to just that. All right. But the one thing that will remain the same, well, actually two things, would be the side opposite the reference angle and the hypotenuse. All right.
The hypotenuse, because it's Pythagorean in nature, it's the sum of the squared values of the legs that make up that triangle. So take a -1, square it, it becomes positive. Square the x squared minus 1, it becomes x squared minus 1. 1 minus 1 cancels out, and you're left with just the square root of x. And really that's it. I mean, I can just show it real quick. So -1 squared plus x squared minus 1 squared is equal to, I'll call it c squared. So 1 plus x squared minus 1, we're looking at x squared is equal to c squared. But again, because we're talking, well, aside from it being a geometric length, we're talking about a cancellation of powers. All right. So we would have x equals c. All right. So no matter where you place it in the appropriate domain or range, depending on how you look at it, you're always going to end up with a positive opposite side and a positive hypotenuse. Now, if you were allowed to go into quadrants 3 and 4, it would be a different story, but that's not the case. So how does that apply here? Well, it tells us that those hypotenuse values, which are represented by x, need to be positive. So if it's guaranteed that it's always going to be a positive result, then I can drop the absolute values. Well, I'll leave it there, just so it's not too mysterious where they ended up. But in doing so, I now am able to cancel a secant. So I'm left with x arc secant of x minus the integral of secant theta d theta. The antiderivative of secant theta d theta is, so we have the negative built in, ln of secant theta plus tangent theta plus c. All that other stuff comes along for the ride. And then we just have to pull a secant ratio out of this. Hypotenuse over adjacent, and a tangent ratio opposite over adjacent. So x arc secant of x minus ln of x over 1, which is just x, plus opposite over adjacent, the square root of x squared minus 1 over 1, which is the square root of x squared minus 1, close it up, plus c. And so that would be your antiderivative. Last one, we have a suggestion you could also refer to a table of integrals like you can find on this link. Sometimes it's a crapshoot, and sometimes you find yourself shoehorning, a strategy where it doesn't always seem to apply. But oftentimes you can sort of catch lightning in a bottle, and that's obviously a good thing. All right. So if you find yourself in that position, then it could be quite a journey. All right. Because if you go down the list and try every single, you follow this table, you go down the list and try to apply one of the rules one at a time, it could be a lengthy process. All right. So what we'll do is we'll just kind of go with what makes sense and then go from there. All right. You could try things like U substitution, but it doesn't always pan out, and so you're going to need some other techniques along the way. All right. I'm looking at this, and I'm just trying to kind of compare it to something I might have seen before. All right. Now, not in this exact same form, but this looks an awful lot like a partial fraction situation. So let, for example, let sine of x be equal to, well, we use u a lot, so let me say r. All right, in which case we'd have r squared plus 2r. That's factorable. All right, now the top is a different story, but we could actually make that work too. All right, but
if we were to factor this, it would be r times r plus 2.
Well, that's a set of linear factors. All right, so we could do the same thing with trig functions. So we're kind of, taking a looser approach to this, but it's sort of like, well, maybe it's kind of sort of reminds me of partial fractions, so maybe I'll try doing it that way. All right, so I'd be thinking about, okay, well, what would I do if it was partial fractions? Well, I'd have some sort of number on the top that I would be looking to. I mean, they're linear factors, so it would be a sub 1 over r plus a sub 2 over r plus 2. Right? That's what I would do. So, okay, well, the r is the sign. So, okay, that could be fun. But you know what we could also do is we could work with it in this form and then later on put the r's back in. All right? So, it's just a question of what we're going to do with that cosine. All right? Well, cosine's got to factor into this in some capacity. So, we could write it as the derivative of sine is cosine, so I could call it r prime if I wanted to. Or I could just leave it as cosine, right? And say, for example, cosine of x over r times r plus 2 is equal to a sub 1 over r plus a sub 2 over r plus 2. And then I would start the cancellation, simplification process, which would involve multiplying everything by r times r plus 2. On the left, I would just be left with the cosine of x. On the right, I would have the a sub 1 times r plus 2 plus a sub 2 times r. Now, it isn't so much that I'm in love with this concept of using an r. It's just that I'd rather write r than writing sine of x over and over again. All right, but eventually you get to a point where you say, well, maybe I don't want to do that so much. So we're at this impasse where it's a question of, okay, well, do I want to put everything back in terms of sines and work with it that way, or do I want to keep everything as is? And if I do that, then I got to do something about that cosine. That cosine, again, can be written, mentioned this before, as the derivative of the sine, because if r is equal to the sine of x, then dr is going to be equal to cosine of x dx. All right, so we have that substitution. Well, actually, really the substitution, force of habit, really the substitution would be dr dx. All right, so I can abbreviate that as r prime, just to make things simpler, is equal to cosine of x. All right, so r prime is going to be equal to a sub 1r plus 2a sub 1 plus a sub 2r. All right, you'll notice on the left-hand side there are no terms that contain just an r. So that's telling me that a sub 1 plus a sub 2 has to be equal to 0. All right, which forces 2a sub 1 to be equal to r prime. All right, so if I solve for r prime, I get a sub 1 equals 1/2 r prime. All right, and we'll keep track of the fact that that's the same as dr dx. All right, so if that's the case, then another substitution would be, instead of a1 plus a2, it would be 1/2 r prime plus a2 is equal to 0, in which case a2 would be negative 1/2 r prime. All right, so I can now say that I have an integral, instead of a sub 1 over r, it would be 1/2 r prime over r plus negative 1/2 r prime over r plus 2. All right, rewriting that, and also bearing in mind that this is just a substitution for this piece here, would imply
that I would have an additional dx along for the ride. So I'll put that integral in blue to indicate that those corresponded with the things that we didn't evaluate with the partial fractions. All right, so just cleaning it up a little bit more, 1/2 dr dx, handwriting, dr dx over r minus 1/2 dr dx over r plus 2 times dx. If you run through with the dx, it's going to cancel out the dx's in each of those numerators. So, cleaning it up further, I would have 1/2 times 1 over r dr minus 1/2 times 1 over r plus 2 dr, which in turn would give me 1/2 ln of r minus 1/2 ln of r plus 2. All right, so I was able to fit that, oh no, plus c. I was able to fit that to the natural log rule. Now, if you go to the table of integrals, you'll see that all those rules are there, and they're all wonderful, but I've always kind of had that a mindset, if you will, that if you didn't know enough to look for a rule, it doesn't really matter if you have a whole list of them in front of you. You won't necessarily recognize them when you see them. All right. Since I know r is equal to the sine of x, I can reverse substitute. And if I want to clean this up further, I can, because there's a common factor of 1/2 that can be pulled out. And one of the log rules tells us that if you have subtraction in an expression, it can collapse down to division. So this would be the same as saying 1/2, or quality 1, ln of absolute value sine x over the square root, so used to saying that from the 1,000 other problems that involve square roots, sine x plus 2, all plus c.
All right, so definitely a bit of a doozy, but manageable. You just have to kind of dive in, and yeah, honestly, it in a lot of ways it boils down to, I call it, I mean very facetiously, the can method of problem solving. Try something, and if it doesn't work, try something else, because oftentimes that's what happens. So, if you take a look at it, and we started with this because it's like, oh, that kind of looks a little bit sort of like partial fractions, so let's give it a shot. If it didn't work, we would have tried something else. All right, so that's a thought.